Hello everyone. So if you remember last time we looked at threshold functions and we saw that for a random graph g of n and p, if 1 over n is much less than p, then we can say that the random graph would contain a triangle asymptotically almost surely. And if p is much less than 1 over n, asymptotically almost surely it would not contain a triangle, the random graph g of n and p. So basically 1 over n would act as a threshold function for existence of a triangle in the random graph g of n and p. So let me remind you then about the threshold function last time. So we saw about threshold function, and the notation that we used was R of n. So we saw that, for the random threshold function R of n for a property A, monotone, basically property A, we define monotone property. Property A. So if you remember, we saw that threshold function must satisfy two conditions. So one of them is if P of n is much less than R of n, then limit n goes to infinity of probability that g of n and p has the property A must be 0. And the second condition, if R of n is much less than P of n, then limit P of G of n and P has the property A as n goes to infinity has to be 1. So these were the two conditions. And so that, in the case of having triangle, the property A is existence of a triangle in the random graph. And if P is much less than 1 over n, then the probability that G contains a triangle is equal to 0. The limit as n goes to infinity. And if 1 over n is much less than P, then the P probability that G of n and P has property A is 1 as n goes to infinity. So now we want to generalize this. So last time we looked at we considered the property A to be existence of a triangle in the random graph. So what about other subgraphs, basically? So if G of n and P, can we say that it contains a square, for example, or other particular subgraphs? So we want to generalize this to a balanced subgraph. Generalization to balanced graphs. So let's first see what is a balanced graph. So for that purpose, first we need the definition of density of a graph. So definition for a graph, let's say H, the density is defined as rho equals E over V, where E is the number of edges of H, and V is the number of vertices of H. Now, next definition, we say H is a balanced graph if no subgraph of H has a higher density than H itself. So for example, a triangle is a balanced graph. Right? So if I consider a triangle, well, what is the density of a triangle? So density is defined as number of edges over number of vertices. So rho is 1. And if I consider any subgraph of this, it will not have a higher density for sure. So for example, let's say if my subgraph is this, for example. So then the density would be 2 edges and 3 vertices, so 2/3. It will be less, but not more. Or let's say if I consider, for example, this as the subgraph, then the density is 1 edge, 2 vertices, 1/2. Again, less than 1, not more. So no subgraph of a triangle would have a higher density than triangle itself, which has a density 1. So for this reason, a triangle is a balanced graph. Now, what graph is not a balanced graph? Let's give an example of a graph which is not balanced. So consider, for example, let's say, again, a triangle, but one vertex here, isolated. So how much is the so consider this one, say consider the following graph. So this is, let's say, the graph. Rho is 3 edges and 4 vertices. This is not a balanced graph since the subgraph that is just a triangle has density rho equals 1, which is bigger than 3/4. Okay, now we want to find the threshold function for a balanced graph. Threshold function for a balanced graph, we saw that if the balanced graph is a triangle, then the threshold function is 1/n, which means n to power -1. Now, let's think about it. If I have a graph with higher density, okay, see, let's say if I have a graph with higher density, for example, this, then in order for G of n and p to contain, let's say, a graph like this, p should be bigger compared to when I have a graph with smaller density. So for this reason, threshold function of this graph, for example, must be bigger compared to threshold function of a triangle. So it makes sense if I say that the threshold function behaves like, let's say, n to power -1 over rho. Because for this one, for example, rho is 6/4, which is 3/2. So this would be n to the power minus 2/3, which is bigger than, for example, n to the power minus 1, which is the threshold function for a triangle. Okay, so I just want to say that it would make sense if our threshold function behaves like n to the power minus 1 over rho. Of course, we're going to prove it. So let me read this and state the result formally. That so theorem, let H be a balanced graph with density rho, then R of n equals n to the power minus 1 over rho is a threshold function for the event that H is a subgraph of G of n and p. Okay, now proof. Now let's remind ourselves about the definition of threshold function. So we need two conditions. If p is much less than r, we have to show that the limit of probability of G of n and p containing h as subgraph is 0 as n goes to infinity. And then we will also have a second condition. So let's first start with the first property. So first, we show if p of n is much less than n to the power minus 1 over rho, then limit as n goes to infinity, p probability that G of n and p contains h as its subgraph equal to 0. Okay. This is what we want to show. So first, let's, if you remember the idea that we did the same thing for a triangle, and to bound the probability that G of n and p contains a triangle, if you remember, we used a union bound. So we considered different events, and we wrote P of G of n and p containing a triangle as union of some events, and then we used union bound. So let's use the same idea here. So let A1 be the event that H is appeared in, let's say, V1 to Vk. Okay, so here I'm assuming H has, let's say, k vertices. And let's say L edges. Okay, H is a balanced graph, so let's assume it has k vertices. Now, H can appear in V1 to Vk, so that's one possibility. Now, another possibility is that, with the same vertices V1 to Vk, we can have more than one copy of H. Why is that? Because, let me give you an simple example. Let's say this is H. Okay, so let's say with vertices 1, 2, 3, 4, let's say we can have this graph or this subgraph in vertices 1, 2, 3, 4, or I can have this one in with vertices 1, 2, 3, 4. So this second graph is also a copy of the first graph. So if H is this is still considered as a copy of H. So what do I mean mathematically when I say copy of H? I mean a graph which is isomorphic to the original graph. Now, and what is the meaning of isomorphic? So that means, if I can find a permutation of vertices from first graph to the second graph, right? So let's say, for example, if you want to show that these two are isomorphic, I can, let's say, define a permutation P, let's say from 1, 2, 3, 4 to itself. And I can send 1 to, let's say, 2, 2 to 1, 3 to 4, and 4 to 3. And then I can say that, let's say I can call this one H1, and I call this one H2. Then I can say that for any two vertices, let's say A and B belongs to the set of edges of H1 if P of A and P of B is an edge in H2. Right? So for example, 1 and 4 is an H in H1, and P of 1 and P of 4 means 2 and 3, and 2 and 3 is an H in H2, and so on. So basically, two graphs are isomorphic if they have same structure. What do I mean by same structure? Yeah, well, that's the exact mathematical definition, that there is an isomorphic between them, meaning that there is a permutation between the vertices of first and second graph, such that A and B is an edge in the first graph if and only if P of A and P of B is an edge in the second graph. So here, because we have no specific information about H except the fact that it has K vertices and L edges, and it's also balanced, of course. We'll use this assumption later. So if I fix, let's say, K vertices, I can possibly have more than one copy of H, like the example that I showed you here. So I can have, for this reason, I can have more than one event, define more than one event to have a copy of H with vertices V1 to Vk. Okay, so I can define A2 as the event that we have also H appeared again with V1 to Vk, but actually another copy of H in the sense that I just explained here. So let me erase this. This was a simple example just to clarify. Let me say also, let A2 be the event that another copy of H is appeared again in the vertices in V1 to Vk, with vertices V1 to Vk. So how many can I have in total? So let's say A, I can call it, let's say, capital C, be the event that another copy of H is appeared in V1 to Vk. So still I'm not changing the vertices. The vertices are still V1 to Vk, but I can have different copies of H with the same vertices. How many copies can I have in total with same set of vertices, with same fixed set of vertices? Well, that of course depends on the structure of H. But at most, I can say that C is less than equal to, let's say, L. And here I can say, let's say, K times K minus 1 over 2, choose L. Where is this number coming from? Well, remember I have fixed my vertices to be, let's say, first K vertices, okay? So how many edges can I possibly have with vertices V1 to Vk? Well, I could have possibly K choose 2, which is K times K minus 1 over 2 edges with vertices V1 to Vk. Now, if I choose L of these vertices, because remember H is supposed to have L edges. So L of these edges, if I choose L of these edges, then that's the maximum number of copies of H. So of course, it's possible that not all of them are copies of H, right? So let's say, for example, if I choose, let's say this is H, for example, okay? And this is vertex 1, 2, 3, 4, 5. So if I said again, same vertices. Now this has 4 edges. So if I choose these 4 edges, let's say, see, this graph has 4 edges. This graph also has 4 edges, but this second graph is not, of course, a copy of this one. Of course, because this one, for example, has an isolated vertex, but this one doesn't. So the fact that I choose 4 edges out of all possible edges would not mean that each of those cases would be a copy of H. But that's the maximum number that I could have for copies of H. So possibly the actual number of copies of H is less than this number. So that's why I said C is less than equal to this number. Okay, so, all right. Now, what have we done so far? So far, we said that if we fix the set of vertices to be V1 to Vk, then I could have possibly C copies of H with vertices V1 to Vk. So, and I could define C events for appearance of those copies of H with vertices V1 to Vk. Now I can change the set of vertices. So of course, remember I have to choose, well, H has K vertices, so I just want to choose K vertices out of N vertices. Remember, we are talking about G of N and P, so we have N vertices in total. So I just want to choose k of them. Well, of course, one option is to choose first k, but of course I have other options as well. Now let's consider different set of vertices instead of V1 to Vk. So similarly, let's say AC plus 1 be the event that a copy of H appeared with vertices, let's say V1, V2, Vk minus 1, and Vk plus 1. Let's say, for example, if I choose these vertices, and then I will have like A2C again, the event and that copy of H is appeared with vertices. Again, same set of vertices, V1 to Vk minus 1, Vk plus 1. Okay, so that's another option for choosing k vertices. And of course, I have other options as well. So how many options do I have in total? And choose k options in total. So the last event would be A, C times n choose k. The event that a copy of H appeared with vertices, say Vn minus k plus 1 to Vn okay. So now what do we want to find? If we go back, we want to do this first. P of G of N and P contains H as its subgraph. So H would occur as a subgraph if either the event A1 occurs or A2 occurs all the way to the last event, which is A C times N choose K sub N C times N choose K occurs. So P of, hence P of G of N and P contains H as its subgraph is equal to P of A1 union A2 union A sub C times N choose K. So of course this is less than equal to sigma P of AI I from 1 to C times N choose K. And how much is each of these PAIs? So for each of them, well, let's look at A1, the event that H is appeared in this. So H is appeared, H is a graph with L edges, and each edge appears with probability P. And so this, and H has a specific structure. So once I fix the structure and I fix the permutation basically, because we saw we could have permutations as well. But once I fix the structure and fix the permutations And that's what I call each AI. Then the probability that H appears here with vertices V1 to Vk is of course P to power L, because that's L edges and everything is fixed. And each edge has appeared with a probability P. So this is sigma P to power L, I from 1 to C times N choose K. So this is C times N choose K times P to power L. So this is the upper bound for the probability. And now how much is this? Okay, so now this is bounded from above by C times N choose K is bounded by N to power K, right? And this one times P to power L. And then this one, I can write it as C times N to power K over L times P to power L. And N to power K over L is 1 over rho times P to power L, because rho is L over K. Density was number of edges over number of vertices for the graph H. Now, what is my assumption? By assumption, P is much less than N to power minus 1 over rho. And what does that mean? That means limit N goes to infinity. P over N to power minus 1 over rho is equal to 0. And this means limit P times N to power 1 over rho as N goes to infinity is 0. Okay, and this is exactly the upper bound for the probability. So if I call this one, let's say star, I can say hence by star, I can say limit P of G of N and P contains H as its subgraph as N goes to infinity is equal to 0. And we are done with the first goal. So remember, we had two goals in order to prove the theorem. We wanted to show that R of N equals N to power minus 1 over rho is the threshold function. So we had to prove two things. Okay, so let me show you. Yeah. So we already proved the first one, that limit P of G of N and P has the property A here means as H as its subgraph as N goes to infinity 0. Now we have to show that if R is much less than P, the limit P of G of N and P having H as its subgraph is equal to 1 as N goes to infinity. So let's go back. Next, we will show that if N power minus 1 over rho is much less than P, then limit P probability that G of N and P contains H as its subgraph equal to 1 as n goes to infinity. To do so, okay, if you remember, we want to use the same idea we did last time for where we had a triangle and we defined indicator random variables for each of the events that we defined, and we already defined them in this case as well. You remember we call them A1 to A sub C times n choose K. So we'll define the indicator random variable for each of them, and then we will look at the sum of those indicator random variables. So to do so, let x1 to x sub c times n choose k be indicator random variables corresponding to the events a1 to a sub c times n choose k as defined above. Okay, and let x equal to x1 plus x2 all the way to x sub c times n choose k. And what do we want to show? We want to show that limit as n goes to infinity p of x bigger than 0 is equal to 1. So if at least one of these indicator random variables is positive, that means h occurs as a subgraph of g of n and p. And in that case, x would be also positive, right? So x is positive if and only if at least one of the xi's is positive, and one of the xi's is positive, at least one of the xi's is positive if and only if h occurs as a subgroup. So look, if you want to find out whether h happens as a subgraph of g of n and p or no, is same as saying that we want to know whether capital X is positive or no. So we want to show that limit p of g of n and p contains h as its subgraph is 1. That means we want to show that limit p of x bigger than 0 is 1 as n goes to infinity. And to prove this, again, we want to use the idea we applied last time. We will show that limit variance x over e of x the whole squared is equal to 0 as n goes to infinity. This is exactly the idea that we used last time. And we proved it as well, that if this limit is 0, then if this limit is 0, variance x over e of x the whole squared is 0, then we can exactly conclude that limit p of x bigger than 0 as n goes to infinity is 1. And that's basically using second method. Remember, we are still in the topic of using second method. So this one is similar to the idea we applied last time. Okay, so now I can say variance x. What is variance x? So this is variance x1 all the way to x sub c times n choose k, which I can write it as sigma covariance, let's say xi xj. and ij between 1 to c times choose k. So if I put that, we have seen it before, and if I put the extra assumption that I is not equal to j, then I have to add these with the variance of individual random variables to get the variance of sum. But if I don't put any restriction on I and j, meaning that I is allowed to be equal to j, then I don't need to include the variance of individual terms. So this sigma covariance will give me variance of the sum. Okay. Now let's see whether we can bound this covariance. Covariance xi, xj. Let's see how much is this. So this is expected value xi, xj minus expected value xi, expected value xj. And this is less than or equal to expected value xi, xj, which is, so xi, xj, each indicator random variable here takes either 0 or 1. So expected value xi, xj will be non-zero only if both xi and xj are 1. So this is 1 times, yep, xi equals 1, xj equals 1. Okay, now what is the bound for p of xi equals 1, xj equals 1? Xi equals 1, xj equals 1 means h occurs, a copy of h occurs, right? In twice, basically. A copy of h occurs twice. Now, it could happen twice with the same set of vertices or different set of vertices. Right? So let me assume that this xi happens. So xi equals 1. Let's say assume ai occurs with set of vertices let's say, for example, T1 to Tk, and Aj occurs with set of vertices S1 to Sk. Now these two sets could have some intersection or no intersection. If they have no intersection, then that means the set of vertices from first and second are disjoint, and in that case covariance will be 0. So I will not have any issue in that case. We also saw that even if there is one element intersection, if the intersection contains only one element, in that case they would have, yes, one common vertex, but they still would have no common edge, because if they have common edge, then they need at least 2 common vertices. So even in that case where the intersection contains only one element, because still there is no common edge, still the events are independent and the covariance will be 0. Okay, so we would be only interested in the case where the intersection of these two sets of vertices contains at least 2 elements. Okay, so now suppose, so let me consider the size of intersection of these two sets. And let me call it, for example, A. Now, if A is 0 or A equals 1, then covariance Ix_j will be 0. Okay, I just explained why. Now, if A is bigger than or equal to 2 now, what would be, okay, I still remember I want to still find a bound for this probability. Okay, xi and xj, well, xi is the indicator random variable for event ai with event, so let me say ai event at age occurs with in set of vertices this, and aj similarly event age occurs set of vertices. Okay, so remember I want to bound this. Xi is the indicator random variable for AI, which is the event that age occurs with these k sets of vertices, and j also k sets of vertices. And each of them also, of course, e edges. Okay, so in total, if there is no common intersection, I would need occurrence of 2 e edges. So occurrence, let me say occurrence of AI and AJ at the same time requires occurrence of 2e edges if there is no intersection between edges. But I can have possibly common edges. How many common edges can I have? Well, I'm assuming that the vertices have a common elements. And now I want to use the fact that H is balanced. So since H is balanced, how many edges can we have with A vertices? So now, since H is balanced, we can have, or it can have, at most, right? At most A times row edges with A fixed vertices. Because if the number of edges would be more than 8 times row, number of vertices, number of edges, if it's more than 8 times row, then the density would be bigger than 8 times row divided by A, which is row. But we know that the balanced graph is not allowed to have a subgraph with higher density than the original. So for this reason, H would have at most A times row edges with A fixed vertex. Okay, so if there is no intersection between edges, I would have 2E edges require, I would require occurrence of 2E edges. But I know that I have at most A row edges. So at least, so I would require at least occurrence of 2E minus A row edges for occurrence of AI and AJ at the same time. Therefore, for occurrence of AI and AJ at the same time, we require occurrence of at least 2E minus A row edges, which would occur with probability P times 2E minus A. Okay, so remember, let's explain the idea. See, I want to bound this covariance term. Of course, my preference is to bound it with a term which is as small as possible. Okay, so if there is no common edge, then I would have p to power 2e as the upper bound for this covariance, which is very good. P to power 2e would be possibly very small. But I could have common edges. Now, if the common edges is too high, let's say if I have two subgraphs where all edges are common, let's say except one of them. So then in that case, I would need, for example, p to power e plus 1. Because I just need, all edges are common, so of course I need p to power e for one subgraph, and the other subgraph, let's say all of them are same, it has only one extra edge, so p to power e plus 1. I need this upper bound to be as small as possible. So p to power 2e, of course, is much better than p to power e plus 1. So if all edges are common, for example, not good news. Well, here, I know that H is balanced. So if H is balanced, and I am assuming that I'm considering the case where the set of vertices have A elements in common, so that means H can have at most A row edges, so it's not E edges. Possibly, of course, depends on A as well. But remember, I told you that I do not like if all edges are common. So this is a good news because my assumption on H being balanced tells me that H can have at most A row edges there, which are basically the common edges. So not too much, at most A row edges. So that means occurrence of AI and AJ would require at least 2E minus these common edges, so 2E minus A row edges. And each edge occurs with probability P, so P to the power 2E minus A. Thus, covariance Xi, Xj less than equal to P to the power 2E minus A row with the assumption. The assumption above, I mean, because we assume that, you know, the number of the two sets of vertices for AI and AJ have A elements in common. Okay, now another question that we have to address is that how many such xi and xj's do we have that they have A elements in common? How many such xi and xj's we have? So my claim is there are at most, let me say C prime times n choose 2v minus a pairs xi xj with AI and AJ events to set up vertices have A elements, have A common elements. Here, C prime is 2K, choose say 2 times, let me write it this way. 2K, choose 2, choose 2E. Okay, let's see how we got these numbers. So first of all, see, remember we are talking about two events that whose set of vertices have A common elements. So we need to choose 2v minus A vertices for AI and AJ altogether out of n vertices. N vertices we have in G of n and p. Now see, AI has v minus A distinct vertices compared to the set of vertices for AJ. Similarly for AJ, it also has V minus A vertices. So in total, we would have 2 times V minus A distinct vertices, but there's also A common vertices, so that becomes 2V minus A vertices that we have to choose out of n vertices in G of n and p. Once we choose the set of vertices, all vertices for AI and AJ all together, which is 2 times V minus A plus A, which is 2V minus A, then we are saying that, of course, we would still have more than one options to construct one copy of H with the set of vertices came in VI, and and one copy of H with set of vertices that comes with AJ. We could have possibly more than one option, but how many such options, once I fix the set of vertices, how many such options do I have? Well, that depends, of course, on the structure of H. But let's say, for example, if I have one common edge, okay, let's say this is the common edge, and then we have, let's say this is H, for example, and this is one copy, and then this is another copy. So I want to say that we can define a one-to-one function or injective function from such a pair of graphs to two graphs where they have no common edges or common vertices. How can I do that? Well, I just need to duplicate the common edge here. So see if I duplicate it here. I will get a pair of graphs with no common edge or vertex. So what does that mean? That means the number of pairs of graphs in the left-hand side where they have possibly common edges or vertices is less than equal to number of pairs of graphs that they have no common edge or vertices. Now, how many pairs of graphs do I have with no common edges or vertices? Well, I have 2K. Remember, I need 2 copies of H with, in the right-hand side, 2 copies of H with no common edge or vertices. So in total, I have 2K vertices. Remember, H has K vertices, E edges. So 2K vertices in total, and I need to have 2 E edges appeared here. So in total, at most, I can have 2E, choosing 2E edges out of all possible edges with 2K vertices. In total, I have 2K, choose 2 possible edges with 2K vertices. I need to choose 2E of them. Then this is the maximum number of having 2 copies of H with 2K vertices. And of course, possibly less than this number. And even the pair of graphs in the right-hand side with no common edges or possible, with no common edges or vertices is possibly less than this number. And the number of such pairs in the left-hand side, of course, as well, will be less than, possibly less than this number C prime as well. But the important thing, so this C prime could be possibly a big number, but the important thing about it is that it's independent of N, and it only depends on E and K. And remember, E and K, number of edges and vertices in H, is fixed from the beginning. H is given, it could be a triangle where E is 3 and V is also 3, or any other fixed graph. E and K are all fixed. Okay. So now that I explained the number of such pairs for xi and xj, we are ready to find the variance and find an upper bound for the variance, basically. So let me erase this part. Okay, therefore, okay, the variance x was, if you remember, sigma covariance xi, xj. The sum was over I and j. And this is less than equal to sigma I and j. And each of these guys we saw was less than p to power 2e minus a rho. And how many such pairs did we say we have? We said we could have at most, with fixed a, we can have at most c prime, I call it c prime, times n, choose 2 v. So but here by v I mean number of vertices. I think I called it k, so let me call it k here as well. So 2k minus a. And then the sum a, we said starts from 2 all the way to k. Now this is less than equal to sigma, so c prime can be taken out. Less than equal to Well, this combinations is binomial coefficient is less than n to power 2k minus a, p to power 2e minus a rho, from 2 to k. N choose k, of course, is always less than equal to n to power k. So n choose 2k minus a is less than equal to n to power 2k minus a. Okay, now by the way, the number of edges I previously denoted with L. So let me correct this with 2L minus a rho, and also here 2L. Also here 2L. The number of edges to be consistent with my previous notation, and now I can simplify this as C prime sigma a from 2 to k. I can write it as n to power k p to power l times 2 minus a over k, right? So n to power 2k minus n to power a, which is what I have here. N to power 2k times n to power minus a, or n to power 2k minus a. And this part is p to power 2l times p to power minus a l over k. L over k is a rho. So this can be written this way. Okay, so this is variance x. Next, so variance x over e of x, the whole squared. So variance x, we already have this expression for it. 2 to k, n to power k, p to power l, power 2 minus a over k. And what is e of x? Well, let's go back to see what x was. X was sum of xi's, if you remember. The x was sum of all xi's. So e of x is sum of e of xi's. And each indicator random variable, you know, it has the property that e of expected value of indicator random variable is same as p of a, where a is the corresponding event. So this e of x is sigma pai, but we already calculated that. Sigma pai was here. See, sigma pai was c times n choose k p to power l. So if you look at here, this is sigma pai. So c times, so divided by c times n choose k p to power l to power 2. Okay, now I can, so c prime is constant, c is constant. So n choose k is order n to power k, right? So I can write, and remember k is fixed. So I can write this one less than equal to, so if I call all constants together, let's call it, for example, d, then sigma a from 2 to k, n to k, p to l, 2 minus a over k divided by n to power k, p to power l to power 2. So we basically use the fact that n choose k can be written in our notation, if you remember, capital theta n to power k. So it's order n to power k, so can replace it n to power k, but of course the constant could change here, so I called it d, the new constant. And we're almost done. So this one is d sigma a from 2 to k. So then I will have n to power k p to power l to power 2 times n to power k p to power l to power minus a over k divided by n to power k p to power l to power 2, and this guy cancels with this guy. So I'll have d times sigma a from 2 to k n to power k p to power l to power minus a over k. Now by assumption here, what do we have? We know that n to power r of n, which was n to power minus 1 over rho, which is n to power, well, rho was L over K, so this is minus K over L, is much less than P. So this means limit n to power minus K over L divided by P as n goes to infinity is 0. And this means limit n to power minus K divided by P to power L is 0, right? If limit of this function is 0, the power L of it also has limit 0, which is this guy here. And this means limit limit n to power minus k times p to power minus l as n goes to infinity is 0. So then if I plug this back here, therefore, so look at this one. D times sigma, let me write this expression, to limit n goes to infinity, d times sigma a from 2 to k, and then n to power k p to power l, power minus a over k, which can be written as limit n goes to infinity, d times sigma a from 2 to k, n to power minus k, p to power minus l, to power a over k is 0. Each of these terms will show that it has limit 0. So to the power a over k still has limit 0. Remember, k is fixed because h is fixed. K was number of bits in h. In the case of triangle, k was 3. And a is some number between 2 to k. So in the case of triangle, k was 3 and a is either 2 or 3. So each of these terms is 0, and the sum, again, because k is fixed, is also 0. Each term is 0, the limit of each term is 0, and the sum is also 0, again, because k is fixed and d is constant. Well, that's it. So we showed that this variance x over e of x the whole squared, this expression, the limit of this expression as n goes to infinity is 0, which was exactly what we needed to show. So we showed limit variance x over e of x the whole squared as n goes to infinity is 0, and this means limit p of x bigger than 0 as n goes to infinity is 1, and therefore we proved both conditions needed to be proved in order to show that r of n equals n to power minus 1 over rho is the threshold function uh, the balanced graph H, or let's say for existence of the balanced graph H with density rho in the random graph G of n. Meaning that if P is much less than R, then the probability that G of n and P contains at least one copy of H is 0 as n goes to infinity, and if R is much less than P, the probability that G of n and P contains a copy of H is 1 as n goes to infinity, which means R of n equals n to the power minus 1 over rho is the threshold function. Thank you very much, and see you next time.